All right. So a couple of announcements to start with. First of all, we are not going to have Lab 4 this week as it was announced yesterday. It's mostly because we are still covering the theory portion for MOSFETs in the class. And you'll require some of those concepts in your Lab 4 as well as Lab 5. So we are not, the deadline for Lab 4 will be next week. I think the TAs are also going to change the deadlines on your canvas if they haven't done that already. But as shown on the syllabus, the Lab 4 deadlines will be next week. Also at the same time, there will be no class this Friday because of homecoming. And on Wednesday, I'm actually traveling, but on the syllabus, it was a review for your midterm exam. So basically, your midterm exam is also going to be a take-home exam, which will be next week. I'll open the exam during the weekend this week, and then you'll have 1 week to submit it, just like the previous exam, as well as some of the homework assignments that you have been submitting. So it will be of the same format, again, 100 marks. There would be about 4 questions, and take home means it's similar to a homework assignment. Okay. On Wednesday's lecture, because I'm traveling, one of our graduate students, and he's also working as a STA for this course, Sajai. So he will be teaching the class on Wednesday. And he will be going over some of the example problems for which are very similar to your homework 4 and will be very important for your midterm exam as well. So it's basically a review for that midterm exam. And he'll be going over some of these example problems, how to solve them, and he'll go over them in the class. Okay. Any questions on labs or midterm exam, which is next week? If not, oh yeah, there's a question.
Pre-lab, just to be clear, pre-lab is still due like 15 minutes before the actual lab.
Yes, that's true. But the TAs will change the deadlines accordingly, right? According to the lab section. So thank you, Shah. Yep. And we'll see you on Wednesday. All right. So thanks, everyone. Now, related to the topics that we were discussing last week, we have covered the basics of MOSFET. You know how the MOSFET structure looks like. You also know how it operates. So, for example, the N-channel MOSFET, as well as P-channel MOSFET. We mostly discuss about the N-channel MOSFET, but the P-channel MOSFET works in a very similar manner. Let me make sure that I'm recording from this Zoom as well. Yeah, I think it's getting recorded and I'm getting the notification. Okay. All right. So last lecture, we discussed about the different operating conditions for MOSFETs. And you know that for an N-channel MOSFET, you need to apply a positive gate bias or a positive gate voltage to, first of all, make the MOSFET turn on. So just like the diode, the MOSFET also has a threshold voltage. And the necessary condition for the FET to be on is that your gate to source voltage, VGS, has to be larger than the threshold voltage. So VGS greater than VT, that's the necessary condition for the MOSFET to turn on. Of course, you can also represent it in terms of overdrive voltage. And again, overdrive is just the additional amount of voltage on top of the threshold voltage required that you can apply at your gate to make sure that the transistor is on. So overdrive voltage, which is greater than 0, that means the gate to source voltage is higher than the threshold voltage and the MOSFET is on. So it's 2 different ways of saying the same thing, that your VGS is higher than threshold or V overdrive is higher than 0. Okay. Now, that's when the MOSFET is on. You also came to know what we mean by the triode region as well as active region of the MOSFET. Again, I'm just repeating this, that if you're plotting drain to source voltage VDS on the x-axis and the drain current on the y-axis. So basically, this is the output characteristic of the MOSFET. And you know that the output characteristic looks somewhat like this, that after a certain VDS, the drain current almost saturates. And we also saw that there are non-idealities. That's why I'm saying that it almost saturates. If it is exactly saturating, then you'll see a curve which is exactly parallel to the x-axis. That does not happen in real MOSFET. We'll also go over that in today's lecture. But this right-hand side region is what we'll be calling the active region or the saturation region. And the left side region, which is valid for small VDS, that is the triode region or the linear region. So the triode region definition is that the MOSFET has to be on, because if the MOSFET is not on, you'll not have any drain current at the output. Okay. So first of all, the MOSFET has to be on. That means VGS has to be greater than threshold. And at the same time, your drain to source voltage has to be small. So on the left side, you have a small VDS. What is the definition? Now, small is a qualitative word. What is the definition of small? The definition of small in this case is that if your VDS is lower than, or let's say less than equal to V over drive, then we say that the MOSFET is in the triode region or the linear region for which the VDS is small. On the other hand, you are in the saturation region. So this is the triode region on the left side. And on the right side, you are in the saturation region. And in this case, you have large VDS. And again, large is a qualitative word. If you want to define it quantitatively, you say VDS greater than V over drive. That's the definition for the saturation region. So that's what we are writing over here, that for the triode region, your MOSFET has to be on. So VGS has to be larger than threshold voltage. At the same time, your VDS needs to be lower than the overdrive voltage. So VDS less than VGS minus VT. Similarly, for the active region, your MOSFET needs to be on and your VDS needs to be greater than the overdrive voltage. And that's the definition of your active region or saturation region. Why do we call it the saturation region? That's because the current is getting saturated, as you see from this graph that we have drawn here on the right-hand side. All right, and we also derived the equations for both triode and saturation region. Again, just a repetition from previous classes. Your ID in the saturation region or in the active region can be represented as ID equal to K over 2 times V over drive squared. What is K? K is called the device transconductance, which is equal to mu times COX times W over N. The mu times COX is called the process transconductance because it is dependent on the particular process technology, the mobility as well as the oxide capacitance per unit area. On the other hand, if you multiply the aspect ratio of the MOSFET with that, so aspect ratio is W over L, and W over L is something that is in your control as a designer. When you're designing any circuit, you can define that, okay, this is the W over L I want, and according to that, the foundry will actually design or actually fabricate the MOSFETs. So anything that is inside your cell phone or in your laptop or your iPad, all those MOSFETs have a particular W over L, and that W over L was specified by the designer during design time, and the foundry prepared the circuit accordingly. Okay. Now, mu times COX times W over L, that will be called the device transconductance. And why it is a transconductance? Again, you know that the left side is a current, the right side is a voltage squared quantity. So it's not a transconductance in a strict sense, but because it is relating the current with the voltage, we still call it a transconductance. So device transconductance is mu times COX times W over L, that is represented by K. And process transconductance is just mu times COX, that sometimes is represented with K prime or beta prime in many books that you might refer to. Of course, VGS minus VT, that's your V overdrive. And this is a simpler way of writing this equation on the left side. So just remember ID equal to K over 2 times V overdrive squared. And that's going to be the most important equation that we learn in this course, I would say. Of course, we also learned the triode region equation. And that is, again, something of this form. You have learned how to derive this as well. You can represent it in a very similar form as what I have written over here. So you can represent it as, let's say, K over 2 times twice V overdrive times VDS minus VDS squared. So it's of the very similar form. You have K over 2 times V overdrive times VDS minus VDS squared. Of course, if VDS is very small, your VDS squared is even smaller. So you can ignore this term. And in that case, your equation becomes ID equal to K over 2 times or K times V overdrive times VDS. So it is proportional to VDS when the VDS is small. but it is independent of VDS when VDS is large. And toward the end of the last lecture, we also looked into channel length modulation. What does channel length modulation say? That again, we kind of hand-wavingly said that in saturation, the current saturates. So ideally, you would expect this out of the MOSFET, that the current is exactly proportional to the x-axis because the current does not depend on VDS in that equation that we wrote in the previous page, that in saturation, your current is equal to K over 2 times V overdrive squared. And V overdrive is just VGS minus VT, so it has no VDS term in it, right? So ideally, the current should have been a constant term with respect to VDS. But as you see that in a real MOSFET, that does not happen. Why does it not happen? That if you remember that, let's see if okay, maybe let's just download the proof of MOSFET IV characteristics once again. If you remember that when we proved that what is going to be the equation for saturation, remember that there was this concept of pinch off, that the channel reduces to a triangular channel instead of a rectangular channel when you are in saturation. And then as you keep on increasing the drain to source voltage, that pinch off point moves towards left. And that means that the effective length of the channel, that is the physical length of the channel is the entire length from drain, source to drain. However, the physical length of the channel is where this channel is present, right? From the source region till the point you have pinch off. When we proved this equation, we saw that this is going to be W over L dash or L prime, where L prime is the effective length of the channel and not the physical length of the channel. Now, some of you asked that, okay, what is the difference and how does it matter? So at that point, I said that let's simplify things for now. Let's just assume that your physical length and the actual length or the effective length are the same. So at that point, we assume that L prime is actually equal to L. And then we wrote this equation, K over 2 times V overdrive squared. But in reality, L prime is not equal to L because, and it is a function of VDS, because if we apply more and more VDS, the depletion region around this PN junction over here will increase or will widen. The other way of saying it that if you increase this VDS, some of these electrons in the channel will get sucked into the drain region, which means that the channel will move towards left or the pinch off point will move towards left. It's like different ways of saying the same thing eventually. So you know that this L prime or the effective length is dependent on VDS, even though we did not consider it when we wrote this equation down. Now, the entire proof will be done in your analog circuit 1 class, which is a graduate level course. But again, I'll give you a simplified view of what happens. That this effective length L prime is a function of VDS. And you can write this L prime as L times 1 minus lambda VDS. What does this signify? That if I have a higher VDS, my L prime will be a lower number because what is this? This is equal to L minus, this is equal to L minus L times lambda times VDS. So originally I had the full length of the channel, the full physical length of the channel, which was L, but now I have an effective channel length, which is a function of VDS. And if I increase my VDS, the effective channel length will reduce. What is that proportionality constant? That is lambda, that if I increase my VDS by some amount, lambda times VDS will be the effect or the impact on the effective length of the channel. So that's why I'm saying L prime is equal to L times 1 minus lambda VDS. And it says that if you increase your VDS, your L prime will reduce. So on your denominator, you now have this L prime. So I can write just this part as, basically you have a 1 upon L prime. I'm not writing the rest of the terms here because I'm only interested in the L prime. So you can write this L prime as 1 over L times 1 minus lambda VDS. Now, all of you know about Taylor series expansion. And if you do a Taylor series expansion of 1 over, let's say, 1 minus A. If you do a Taylor series expansion of this, you can write this as almost equal to 1 plus A, right? So by the same logic, what you can write here is that this 1 over L times 1 minus lambda VDS is nothing but 1 plus lambda VDS divided by L. So you have this 1 plus lambda VDS term now in the numerator. Instead of having a 1 minus lambda VDS term in the denominator, you can have a 1 plus lambda VDS term in the numerator from this property of Taylor series expansions. And what that means is that now you can write W over L prime, and you can represent L prime as L times 1 minus lambda VDS. And that will eventually give you this additional 1 plus lambda VDS term in the numerator with W over L represented as like exactly as W over L and not as W over L prime. Right? You just replace L prime with this function of VDS. Now, what does that leave us? That you have another additional 1 plus lambda VDS term in the numerator. So you represent your ID as half mu n COX times W over L prime times V over drive squared, or you represent that as half mu n COX times W over L times V over drive squared times 1 plus lambda VDS, because this 1 plus lambda VDS will be in the numerator. So if we do that, then we have this equation over here, which just tells you that ID is equal to K over 2 times V over drive squared multiplied with 1 plus lambda VDS. So this is the additional term that takes care of the channel length modulation. This is called channel length modulation because your effective length of the channel is changing as a function of VDS. And that is the reason why, even though to the first order we assume that the MOSFET in saturation is not a function of VDS, it is a weak function of VDS. This lambda, generally the value of lambda is in the range of 0.1, 0.05, or in a similar range. So it's a very small number, but it is still dependent on VDS. And it is called channel length modulation because your effective length of the channel is being modulated or changed or modified as a function of VDS. But again, to the first order, the MOSFET ID is K over 2 times V over drive squared or VGS minus VT whole squared. And that is the reason why the MOSFET is called a square law device, or this model is called a square law model, because your current is square of the V over drive squared, or basically square of the V over drive, or VGS minus VT. All right. Now that we know that in saturation, our current is not parallel to the x-axis. If it were parallel to the x-axis, what would have been the output resistance? Of course, you know that the output conduct, what is the output resistance? Resistance is del V over del I. Right, the derivative of voltage with respect to current, that will give you the resistance. Now, both of these quantities are at the output. This is your output current. This is your output voltage for the MOSFET. So if you take del VDS over del ID, that will give you the output resistance of the MOSFET. You can represent this as 1 over del ID over del VDS. And del ID over del VDS is nothing but the slope of this curve. So this is 1 over slope. That will be equal to the output resistance. So let me just call that RO of the MOSFET, which is equal to del VDS over del ID, which is 1 upon slope. Now, if you had this ID exactly parallel to VDS, what would have been the slope? 0. Right? A curve which is parallel to the x-axis has a slope of 0. 1 upon 0 would have been infinite. So your output resistance would have been infinite. And that is perfect because for a current source, you know that the output resistance needs to be infinite. An ideal current source has an output resistance which is equal to infinite. So if the MOSFET had a perfect slope, zero slope in the saturation region, it would have had infinite output resistance. But in reality, it does not have infinite output resistance. Still, it has very high amount of output resistance. What is the value of that output resistance? We can just calculate because we know the equation of ID. You know the equation of ID as a function of VGS and VDS. Now, oops, now if you find out del ID over del VDS, so basically a derivative of this above equation with respect to VDS, you can, I'm not going through the derivation and what formulas are used for derivation. Again, assuming that you know this from your high school math, del ID over del VDS is equal to lambda times half mu and COXW over L times VGS minus VT whole square. Why is that? Because this one term that becomes a constant and it gets, the derivative of a constant is 0. So there's no impact of this first term. The second term is lambda VDS. So lambda will stay as you're taking the derivative with respect to VDS times this entire quantity. That's what you're going to get as del ID over del VDS. Now this is del ID or lambda ID divided by 1 plus lambda VDS, right? Because this was your ID divided by 1 plus lambda VDS, and then you have a lambda term multiplied with it. So you have lambda ID divided by 1 plus lambda VDS. So that represents the slope of this ID versus VDS characteristics. Now, if you just approximate that as lambda ID, because 1 plus lambda VDS is going to be very close to 1. Lambda is very small, so lambda times VDS is still going to be very small, and 1 plus lambda VDS is going to be very close to 1. So if we approximate this as lambda times ID as your output conductance, the output resistance will become 1 over lambda ID. And because lambda is a small number, ID is also, in most cases, will be in microampere or milliampere range. Your 1 upon lambda ID is going to be a large resistance. Ideally, it would have been infinite if the slope would have been 0. But in reality also, it's a large number, which is given by 1 upon lambda ID, as we found from the equations. So what did we learn here? That the output resistance of a MOSFET is equal to 1 over lambda ID. Now, in the mathematical, in the problems, if I give you lambda equal to 0, then you know that RO is going to be infinite anyway, because 1 upon lambda ID is going to be infinite if lambda is equal to 0. So in the questions, if lambda equal to 0 is given, you know that things are simplified and RO is going to be infinite. And the saturated or ID versus VDS characteristic is going to be exactly parallel to the x-axis if lambda is equal to 0. All right. Let's also quickly take a look at the voltage transfer characteristic of the MOSFET if the circuit is looking like this. Now you have already looked into voltage transfer characteristic for an op-amp and you have an idea of what it might look like. But of course, in this case, let's try to find that out from the equations that we just learned. That your ID is equal to K over 2 times V over drive squared, neglecting the lambda parameter for now, let's say. In most problems that we'll solve in class or in the exam, lambda will be given to be 0. But I said most, but so that's why just keep a lookout for whether lambda is given to be 0 or not. If I give lambda is non-zero, then of course you need to find the RO parameter and the effect of the lambda parameter. But ID equal to K over 2 times V over drive squared. Basically, for the MOSFET, if you're applying a VGS voltage at the gate, you know that is the current that is going to flow through the MOSFET, assuming that the MOSFET is in saturation. Now, that's a big assumption. Of course, we need to make sure that the MOSFET is in saturation, and that's what we mean by biasing. When you say biasing, that means we want the MOSFET to be in saturation. Now, if the MOSFET is in saturation and if this is the current that is flowing through the MOSFET, that's the same current that is flowing through this RD resistance because of KCL. Now, the drop across this RD resistance will be RD times that current. Okay? And the drop across the MOSFET, which is VDS. What is the drop across the MOSFET? That's the drain to source voltage, right? The drain is over here and the source is here. Remember that the source always has this arrow. So the source is the bottom terminal and the drain is the top terminal for the MOSFET. And VDS is going to be VDD minus ID times RD. VDD minus the drop across this resistance will give you the VDS. So of course, what that means is that if your current is larger, your VDS is going to be smaller, right? VDS is, let me clear all of this up. VDS is equal to VDD minus ID times RD. If current is larger, your VDS is going to be smaller. When is the current larger? Current is equal to K, half of K times VGS minus VT whole square. So if your VGS is larger, your current will be larger, and then your VDS is going to be smaller. And again, that is the reason why your VTC looks like this, that if you keep on increasing your VGS, which is your input voltage presented at the x-axis, the output voltage, which is VDS presented on the y-axis, that is going to reduce. However, there would be a few other regions of operation. For example, your x-axis is VGS. You know that if VGS is less than the threshold voltage, the MOSFET will be off. There will be no current through the MOSFET. If there is no current through the MOSFET, there will be no current through the resistance. And if there is no current through the resistance, the drop across the resistance will be zero. That means the entire current, entire voltage drop will happen across the MOSFET if the MOSFET is off. If the VGS is less than the threshold voltage for the MOSFET, that's when you have the cutoff region. And then the drop across the MOSFET will be the entire voltage that you have over here, which is VDD. So this is the region when you have cutoff, that your VGS is lower than the threshold voltage. VGS is between 0 and VT. There is no current through the MOSFET or very small amount of leakage current through the MOSFET. And in that case, the entire voltage drop, almost this entire voltage drop is happening across the MOSFET. So your VDS is equal to VDD in the cutoff region. Then when your VGS is just higher than VT, let's say you just cross the threshold voltage, then your MOSFET will turn on, right? That you have just crossed the threshold voltage, so the MOSFET turns on. Which region does the MOSFET turn on? The MOSFET is going to turn on in the saturation region. Why? Because your VDS is large. Remember that when you are in the cutoff region, your VDS, the drain to source voltage, was a large voltage. It was equal to VDD, the entire voltage that you have in the circuit. And we learned that when VDS is large, you are in the saturation region. When VDS is small, you are in the triode region. What is the definition, quantitative definition of small versus large? If VDS is less than overdrive, you are in triode. If VDS is more than overdrive, you are in saturation. But remember that when your VGS just crosses VT, your VDS was still very close to VDD. So it must be much larger than the V overdrive, because V overdrive is VGS minus VT, which is just becoming positive at this point. So it's very good. V overdrive is very close to 0 over here, and VDS is very close to VDD over here. So which means at the point when you turn on the MOSFET will turn on in the saturation region. It will not turn on in triode. It will actually go from cutoff to saturation directly. And the reason behind that is that the point where you cross your threshold voltage, your V overdrive just becomes positive, whereas VDS just becomes a little smaller than VDD. So VDS is still much, much larger than V overdrive, which means you are in the saturation region. Okay. So you turn on the MOSFET in the saturation region. And then, of course, according to this equation, this is the equation for saturation current for the MOSFET. And then as you keep on increasing your VGS, your current keeps on increasing, which means your VDS keeps on reducing. So your VDS will keep on reducing in the saturation region till the point you hit triode. What is the definition for triode? That again, if you're, so let me write that down over here. What is the definition for triode region? That your VDS is small. Your VDS is less than your overdrive voltage. So as you keep on reducing your VDS, also at the same time, you keep on increasing your V overdrive, because on the x-axis, your VGS is increasing. That means your overdrive voltage, which is VGS minus VT, that's also increasing. So you have both the effects at the same time. On your x-axis, your overdrive is increasing. On your y-axis, your VDS is reducing at the same time. There would be a point when VDS will become lower than VDS. And that is the point when your device will go into triode region. So after this point B, this region is where your device is going into triode. So that's how the voltage transfer characteristic, or VTC, looks like for the MOSFET. Of course, you know already from your op-amp discussions that you'd like your op-amp or MOSFET to be biased in the middle of the VTC curve. So maybe somewhere over here. Why? Because at that point, the slope is maximum. And if the slope is maximum of this curve, you know that the gain of the MOSFET or the gain of the op-amp will be maximum. Right? And that means that you want your transistor to be in the saturation region for your gain to be maximum. You can be in the cutoff, you can be in the triode, but that just means that your gain will not be maximum because the slope of this curve is not maximum in the other regions other than the saturation. For example, in cutoff, the slope is 0. In triode, the slope is again very close to 0. So you want your transistor to be in saturation for the slope to be maximized. That means the gain to be maximized. And that is the whole meaning of biasing, that unless you bias your transistor in the correct region, the transistor will not work. If your transistor has a VGS very close to 0 and a VDS very close to VDD, you cannot expect gain out of the transistor because you'll be here. If your gate to source voltage is very, very large and your drain to source voltage is very, very small, you are somewhere over here and you cannot expect gain of the transistor out of the transistor because your slope is very close to 0. To have your slope the largest number, you want to be somewhere over here. And that is the meaning of biasing, that I want my VDS to be somewhere in between 0 and VDD, maybe around the midpoint. And I want my VGS to be somewhere in between 0 and VDD, again, somewhere near the midpoint. And that's where I can expect the transistor to give the maximum amount of gain. Okay. All right. This is just a graphical representation of what I just said, that if you are in this region, then if you're applying input, let's say something like this, and in this case, the triangular wave is just represented as an example. Because the slope is, or the absolute value of the slope is larger than 1, the output will, or the gain will be larger than 1, and at the output, you'll see a larger triangular wave. Of course, because as your VGS is increasing, your VDS is reducing, you have a 180-degree difference between your input and output. And that's why when we were discussing op-amps as well as MOSFETs, we told that the gain, sometimes you'll see the gain is negative. What that means is that there is a 180-degree phase difference between your input and output, which means if your input increases, your output will reduce. And that's what we saw in the earlier slide as well, that if your input voltage increases, your output current increases because output current is proportional to input voltage squared. And if output current increases, output voltage will reduce because the output voltage was VDD minus ID times RD. All right. So that's what you'll expect when the transistor is in saturation, and we expect a good amount of gain out of the transistor. Of course, your input needs to be a small quantity. If the input is very large, let's say the input is moving between here and here, what would happen? That when the input is smallest, you're kind of in the cutoff region. When the input is very large, you go into the triode region. Right? If your input is very large, then there is a possibility that the MOSFET goes into triode and saturation in the peak and trough of the inputs. And that is the reason why you want your input to be small, to make sure that your transistor is in the saturation. And that is the reason why you might also heard about this term small signal analysis. So what does small signal analysis mean? That you want to analyze the gain of the transistor, but you're assuming that the input is a small signal. That's because you want your transistor to be in saturation throughout the operation of, or throughout the time when you're applying the input. And if the input is not small, you may go into triode or you may go into cutoff regions, which is not the ideal intended operation of the MOSFET. Question? That's a great question. So again, from this curve, you can actually draw the output in that case, and you'll see that there will be clipping of the output, right? So let's just assume that you have a sine wave. You have a large sine wave, and then you are trying to multiply, you're trying to amplify that to an even larger sine wave. But you are getting clipped by the supply rails, the VDD and the ground. If your VDD is even higher, then you can accommodate for this large sine wave. But if the VDD is a particular value, let's say here, then you'll not even see this region of the sine wave. It will be clipped. Similarly, if this goes below ground, it will be clipped. And that is basically called non-linearities. Because when do you call the output is linear with respect to input? When you have a let's say a fixed amount of gain, let's say gain of 10. And for every value of input, your output is 10 times of the input, which is not true in this case because at the peak and the trough of the sine wave, your output is not 10 times of the input. So in that case, it is called that the transistor or the amplifier has become non-linear. If you want your amplifier to be linear, that means that the gain is fixed for every value of the input. Questions?
So if we were to think of this like an amplifier, your input is basically the voltage across gate to source, and your output is the voltage across drain to source.
Yes, in this case, it is the input and output. And again, as we discussed during when we were discussing the different terminals of the MOSFET, you know that there are 3 terminals. If we ignore the body terminal, of course, you have to keep one terminal as reference, as common, which is the source in this case. You apply the input at the one of the other terminal, which is gate in this case. So VGS is the input voltage, and you look at your output across drain and source. Drain is the other terminal, and source is the common terminal. So this becomes your output. Right? Yeah. All right. So now we know about what do we mean by small signal operation, right? Small signal means we want to do an AC analysis. Again, what does AC and DC analysis mean? That when you want to know whether the transistor is in the correct operating point, when you want to know the transistor is at correct operating point, that means whether the transistor is in somewhere in this saturation region, somewhere in this region where you have the highest amount of gain. And for that, you want to bias the transistor with a particular VGS and particular VDS. That means you want a particular VGS to be applied, and with respect to that, you'll inherently generate a particular amount of VDS. Till now, you're not applying any AC signal. Let's say this AC signal is not even there. You just want to bias the transistor or fix the value of VGS and VDS in a way that you know that when you apply an AC signal, you'll get gain. That is what is meant by biasing. And to do that, you'll do something called a DC analysis of the MOSFET. That you analyze the MOSFET with respect to DC, because right now there's no AC. If you do not apply any AC, you're only interested in the DC, and DC means just the biasing part. Now, when the biasing is done, you want to know how much gain your transistor gives you. And that is called the AC analysis or small signal analysis. Again, why AC analysis? That's trivial because you are applying an AC at the input and want to find out what is the gain that you have. At the same time, you want your AC input to be small, and that is the reason why it's going to be called the small signal analysis. Okay, so that's the nomenclature or meaning of the name, that what is meant by AC analysis, DC analysis, small signal analysis. And sometimes DC analysis is also called the large signal analysis, because in that case, you're not looking at that small signal AC anymore, right? All right. So now when you want to do a small signal analysis of the MOSFET-based amplifier, you want to know the transfer function from the input to the output. We have looked into what does ID versus VDS looks like for us, right? Your VDS is this, and ID is the output current, which may look like this. And you know that the output current kind of saturates at large enough VDSs. But that's just the output. That's what is happening at the output. If you're interested in gain, you want to know the transfer function from the input to the output. So how does that transfer function looks like? Of course, you know your ID is K over 2 times VGS minus VT whole square, right? That's just the overdrive voltage. So VGS minus VT whole squared. So you know that if you increase your VGS, which now in this curve is represented in the x-axis, your ID will increase, and ID will increase as a squared term. ID equal to K over 2 times VGS minus VT whole square. If VGS is in the x-axis, your ID will increase as a squared term. So basically, this is the equation of a parabola, right? When you have a square term representation of the x-axis, if your y-axis representation is square of the x-axis representation. So this is what is connecting your input voltage VGS to your output current ID. You also know about a particular term which connects the input voltage to the output current, and that is called the transconductance. We learned about this when we learned about op-amps, that the op-amp input could be voltage or current, output could be voltage or current, and the gain, which is output over input, can be voltage over voltage, voltage over current, current over voltage, or current over current. In this case, because your output is a current, ID is the output current of the MOSFET is a voltage controlled current source, and the input is the voltage control, which is VGS. So if you take a derivative of ID with respect to VGS, if you take a derivative of ID with respect to VGS, you'll get the transconductance, right? The term that connects your input voltage to your output current. And why are you taking a derivative? That means that if we have a very small change in the input voltage, how much would my small change at the output current will be, right? That's what is determined when you say that, yeah, I'm analyzing it with respect to the derivative. So if you take a derivative of this equation, ID equal to K over 2 times VGS minus VT whole squared, you get K times VGS minus VT, right? Because the derivative is with respect to VGS. The VGS is a squared term. So of course, there was a K over 2. So the squared term will generate a constant term 2, which will get cancelled out with the denominator. So you get K times VGS minus VT if you take the derivative, or K times V of V. So again, as you see that it's a very, very simple equation. GM is equal to K times V of V. And that's the transconductance of a MOSFET. All right. Now you can also represent the transconductance into various other forms. The K times V of V is the simplest one to remember. So let's just write that down, K times V of V. Now you can also know that ID equal to K over 2 times V over drive squared. Right? K over 2 times V over drive squared. That's your ID. So if I write twice K times ID, that is going to be equal to K squared times V over drive squared, right? So ID equal to K over 2 times V over drive squared. I just multiply 2 times K in the left side as well as right side. So you get twice K times ID equal to K squared times V over drive squared. Now your GM was K times V over V. Here on the right hand side, you have K squared times V over drive squared. That's just the square of your GM. So you can also write your GM to be equal to square root of twice K times ID. So this is another representation of your GM, which is exactly the same equation. It's just a mathematical manipulation on the first equation. So K times V of V is equal to square root 2 times square root of 2 times K times ID. And you can also write that as 2 times ID over V of V. So what is 2 times ID over V of V? So from this equation over here, ID equal to K over 2 times V over drive squared, you can take 2 times, multiply the left side with 2, and let's say divide that by V of V. And that would be equal to, on the right side, K times V of V, which is equal to GM. So K times V of V, which is equal to 2 times ID over V of V, or V over drive, are equal to the square root of 2 times K times ID. All three of them represent the same thing. All three of them represent your transconductance GM. So why are there three equations then? I mean, why am I even talking about three different equations if they mean the same thing? That is because in some of the problems, you might see that your V overdrive is fixed. Now, K is something that is mu(n) times COX times W over L. Let's say as a designer, you have already fixed your W over L. Okay. And mu and COX are already fixed by the process, by the foundry. So K is fixed. Now, if you want to have a fixed V overdrive, you can find out what is going to be your GM from this equation very easily, K times V overdrive. On the other hand, instead of fixing the V overdrive, if you want to fix the current of the circuit, then you can find out the GM from the second equation very easily, square root of twice K times ID, because you want to fix the current. And if that current is a constant number, whereas V overdrive is not a constant number, it's hard to find out GM from the first equation because V overdrive is not a constant. Whereas if you have your ID as fixed and constant number, it's easier to use the second equation. On the other hand, if your K is not fixed, however, if your ID and V overdrive both are fixed, then you can use the third equation to find out GM. So there are multiple degrees of freedom when you are designing a circuit. You can have different amounts of V overdrive. You can have different amounts of current. You can have different W over Ls, which will change your K. So as a designer, you have many different combinations of these quantities. And depending on which quantity is fixed and which quantity is not fixed, you can use one particular formula of GM over the others. It will be clearer when you solve analytical problems, which will be done in a Wednesday's class by Shah. But you see that all these three equations actually talk about same thing. They are exactly the same equation. They are not different equations. But it's just that sometimes if in the problem the V overdrive is given and it is fixed, it's easier to use the first formula. So let's say ID is not given in the problem. Can you use the second equation? You cannot, right? So you use the first equation. If V overdrive is not given in the problem, but ID is given in the problem and K is given in the problem, of course you'll use the second equation. And if ID and V of V is given in the problem, K is not given in the problem, you'll use the third equation. Okay? All right. So that's about GM. Now, one thing that we learned, we already talked about this a little bit when we were discussing op amps, that what is eventually going to be the gain of the circuit. You know that what is gain? The gain of this circuit is the output voltage over input voltage. Let's say you are talking about a voltage gain. You are applying a voltage at the input. You want to take a look at the voltage at the output. So you want to look at the voltage gain of the MOSFET. And in this case, the MOSFET is being used as a voltage amplifier. So output voltage divided by input voltage is your voltage gain, right? From the very basic, simplest of definitions, output voltage divided by input voltage. What is your output voltage? Your output voltage, in this case, and remember, in this case, we are only interested, let's say we are interested only in the AC voltages and currents. Why are we interested in the AC voltages and currents? Because gain is always about AC voltages and currents. Gain is never about DC voltages and currents. Okay? When you talk about gain, it's always the AC gain that we talk about. So you are applying an AC voltage at the input, assuming that the transistor is already in saturation. You are already, if this is your VTC, let's just assume that you're already in this region where the transistor is in saturation and you get the maximum gain out of it. So let's just assume that the DC analysis has been done, which is not yet done in reality. It will be done in Wednesday's lecture when you see the problems or the mathematical equations being used to solve those problems. Now let's just assume that the DC analysis has been done and the transistor is in saturation. So you're applying an AC voltage at the input. So your input was VGS, that's your x-axis. You're applying a small perturbation, a small sine wave, let's say, at the input, or a small triangular wave at the input. At the output, you'll see a similar amount of perturbation depending on the gain. What is that output? What is that perturbation at the output? It will be the perturbation in the output current multiplied with this resistance. There is all the output current that is flowing through this MOSFET. The same current will flow through the resistance. So any perturbation in the output current of the MOSFET will also be a perturbation in the current through the resistance. There will be a small amount of change in the resistance as that current is changing because your input voltage is changing. So that current, that small change in the output current multiplied with the resistance, that will give you the change in the output voltage from Ohm's law, because current multiplied with resistance is voltage. So your output voltage quantity, VDS, and here we are not talking about the DC voltage between drain and source. We are not talking about the DC voltage between drain and source anymore. See, we are using lowercase VDS. What lowercase VDS means? That you are only interested in the AC quantity. What is that lowercase VDS? That's the change in the output voltage. Change in the output voltage is change in the output current multiplied with change in the or multiplied with the resistance in this case, which is fixed. So let's say this RD, that is the fixed resistance, multiplied with the change in the ID. Now, why do you have this minus term? Of course, as you saw from our previous analysis, that as your input voltage increases, your output current increases and your output voltage decreases. So that's why you have the negative term over here. Now you already know that your GM is a small change in your output current divided by a small change in your input voltage. So this is del ID over del VGS, or I'm just using the lowercase ID over lowercase VGS to represent that. So ID over VGS is your GM. which means that AV or the voltage gain is nothing but minus GM times RD. So this is another equation that we are going to use heavily when you are doing AC analysis of the MOSFET, that the voltage gain is equal to minus of GM times RD for this kind of a configuration of the MOSFET, which is called the common source configuration, as we'll see in the next Monday's lecture. So those are about all the definitions that we wanted to know. Now, with that, you can create a small signal AC equivalent model of the MOSFET, just like we did for the op-amp. That if you have a VGS and AC voltage at the input VGS, your output AC current is going to be GM times VGS, because transconductance times input voltage gives you output current. Also, you can represent the output resistance of the MOSFET with a parallel resistance of this current source, which is given by RO. And RO is something that we already found out, which is equal to 1 upon lambda ID. That's the output resistance of the MOSFET. So you can find out your ID, which is half of K times V over drive squared. You can find out your GM, which is del ID over del VGS or lowercase ID over lowercase VGS. And you can find out your gain to be equal to minus GM times RD. These are the equations that we'll be using to solve AC parameters, which we will see in next Monday's lecture. But on Wednesday's lecture, Shah will be helping you to solve some of the problems which are similar to homework number 4. And this is already uploaded on Canvas. So you can also go over it before you come to class on Wednesday, which will help you to understand how to solve these problems in a quick manner. Okay, so we'll stop here and we'll discuss some of these problems in the next lecture, which will be very important for your midterm exam next week. Yeah, sure. Okay.